Dr. Katie Altieri from the Oceanography Department, and this is the first lecture in the Principles module, and this is the introductory lecture. So lecture 1, Introduction to Principles of Oceanography. Today's going to be a brief overview of some basic concepts related to the ocean, and these are all connected to the textbook reading that I assigned to you on the lessons tool that you can also find in resources. So a quick overview. The world ocean is the absolutely most prominent feature on Earth if you look at Earth from a distance. It might not seem that way when you're in the middle of a continent, but it is definitely the most dominant feature. The ocean covers almost 71% of Earth's surface, and the ocean is thought to be responsible for the origin and development of life on Earth. And we'll talk about this more when we get to lectures on origin of the ocean and origin of the atmosphere. And the oceans haven't actually been on Earth the entire time for Earth's history, but they've been here for a very long time. And again, we'll talk about this more when we get to the origin of the ocean lecture. The Earth's largest habitat is on the ocean, and the ocean holds over 97% of all of Earth's surface water. And that's shown really nicely with this simple schematic here showing a circle that represents all of Earth's liquid water, and then the smaller circle that shows the fresh water, and then the really tiny circle that shows lakes and rivers. Everything else that makes up that big circle is the ocean. And the ocean is referred to singularly because it really is one ocean. You can travel, you can stay on a boat and travel pretty much everywhere around the entire world's ocean. We divided into the principal, what the textbook considers the 4 principal oceans here, based on some geographical separations from the continents. So you have the Pacific Ocean, which is the largest and the deepest, nowhere near us here in South Africa. And then the Atlantic Ocean, which is slightly smaller, but that's the ocean that's on our west coast. And then on the east coast of South Africa, we have the Indian Ocean, which is primarily in the southern hemisphere. And then far away from us in the north is the Arctic Ocean, which is fairly small and shallow as compared to some of the other oceans. And then south of us, we have what's known as the Southern Ocean. And the reason this isn't considered a principal ocean is because the Southern Ocean is really made up of the furthest south portions of the Pacific, Atlantic, and Indian Oceans. And so in some ways, it's a bit of an artificial barrier. But in reality, there's a really strong ocean current that circumnavigates the Southern Ocean that provides a sort of separation that makes it so it makes sense that the Southern Ocean is considered separate from the Pacific, Atlantic, and Indian. So on the left is a simple pie chart showing the contribution of the Earth's surface that's covered by ocean versus the land. And then on the right, what you can see is the relative size of each ocean basin. So the Pacific really is the biggest by far, and then the Atlantic Ocean, the Indian Ocean, and then the Arctic Ocean is quite small. And it's difficult sometimes to always see this looking at map projections because of the way that we're sort of forced to represent the globe on a 2D surface. And we'll get into that also a little bit more when we look at different map projections. On the left is an idea, is a chart showing the average depth of the various ocean basins. So on average, the Pacific is the deepest at 3,940 meters. And then the Atlantic and then the Indian are pretty similar. And then the Arctic is much shallower. But of course, remember that this is an average. So in order for there to be an average depth of almost 4 kilometers, you're going to have a lot of areas that are much, much shallower and a lot of areas that are much, much deeper. And if we look at the chart on the right, it shows a comparison. On the top panel is the average height of land in green, so that's here, as compared to the tallest mountain, which is Mount Everest. And then those two heights are compared to the sort of deepest features of the ocean. So the Mariana Trench is considered to be the deepest area of the ocean. It's 11,022 meters. And just note how that 11,000 meters compares to the 3,000 meters of the average. And then the average depths of the oceans there next to it. And what you can see is that the tallest features on land pale in comparison to the depths of the ocean. So you could throw basically all the continents into the ocean and you wouldn't see anything. Even Mount Everest wouldn't stick up out of the deepest parts of the ocean. So just to recap, the Pacific is the largest. It accounts for more than half of Earth's surface. It's the deepest, and it's sort of the most dominant feature when you look at a map of the Earth. The Atlantic is much smaller and slightly shallower. The Indian is smaller still, although it's roughly the same depth as the Atlantic Ocean. We probably know the least about the Indian Ocean when it comes to sort of local biogeochemistry or oceanography. And the Indian is one of the only oceans outside of the Southern Ocean that's primarily in the Southern Hemisphere. The Arctic Ocean is really dynamic and really important for climate, but it's quite small in terms of its total size. And again, it can look bigger than it is on a two-dimensional map projection. It's the shallowest because of the way the continents surround the Arctic Ocean. There's a lot of continental shelf. And it's, at least at the moment, permanently covered by a layer of sea ice, a few meters thick in quite a large area of the Arctic Ocean. In contrast, the Southern Ocean is quite large. It circumnavigates Antarctica, and other than Antarctica, there's very little there's no continental influence outside of Antarctica. And it makes up the Pacific, Atlantic, and Indian southernmost extent, so everything south of 50 degrees south. You also sometimes hear this concept of the seven seas in oceanography. So, of course, there are smaller inland seas that are not as big as the ocean, not as deep as the ocean. But these are salty bodies of water, typically enclosed by land except for the Sargasso Sea. And in order to be a sea, there has to be some direct connection to the ocean. So it's the saltiness and the connection to the ocean that separates a sea from a lake, for example. And here, showing the average ocean depth as 3.6 kilometers as compared to less than 1 kilometer for the average continental elevation, just highlighting that sort of depth of the ocean as it compares to the height of land, and the deepest trench as compared to Mount Everest. So that's a super brief introduction to sort of what the main aspects of the ocean are, and I hope you guys all watched the 2 short videos I put on lessons as well. So what is oceanography exactly? It's not just about naming the oceans and figuring out how deep they are. Oceanography is one of the really interesting interdisciplinary sciences because it's the scientific study of all aspects of the marine environment. And by all aspects, it includes so much. There's the geological aspects of oceanography, so coastal processes, sand, beaches, sediments, seafloor tectonics, plate tectonics, volcanoes, all of that stuff. There's the geography, the biology, and I know quite a few of you, I'm sure, are doing marine bio at the moment. There's the chemistry of oceanography, which we're going to talk about a little bit in this course, and then for those of you who take 2005 marine systems, there'll be a lot more on the chemistry. So this is all about the dissolved species, temperature, stratification, density, chemical tracers. And then it connects quite closely to biology, right? Because a lot of this chemistry is about providing nutrients or things that the biology needs. The physical oceanography we'll go into quite a lot in this class. So what are currents? How does the ocean circulate? What are waves? And early on in the principles, we'll talk a little bit about sonar and sound in the ocean and thermal properties. And there's also astronomical aspects of oceanography in terms of understanding tides, which we'll learn about in this class. We won't talk about oceans on other planets, although they're very cool, but we will talk about the origin of water and the origin of life, which requires getting into the formation of the planet itself and what was happening essentially in outer space, which is quite cool. And we're also going to be presenting a lot of scientific information, and I think it's important to just ground ourselves in how we generate this kind of research, particularly in a field such as oceanography that's fairly young. Some of the great pioneers of oceanographic research, or who we think of as the great Western pioneers of oceanographic research, are still alive, because it really wasn't until the World Wars that a large-scale global effort was made to understand the ocean. And so as a result of it being a young science, it can be sort of ever evolving fairly rapidly. And this is based on the scientific method. And so the way scientific inquiry works is that we know that natural phenomena are governed by physical processes, and that the fundamentals of these physical processes shouldn't be different today as they were in the past. And so the whole point is try to understand these processes. And then if you think you understand it, you should be able to make a prediction based on it and test that understanding. And this is the basis of the scientific method. So it all starts with making observations. And so I'm going to try to have an emphasis throughout the course on sharing actual observations with you guys. You know, what's been found when we go out and look at this particular thing in the ocean. And from those observations, there are hypotheses generated. And then once you have a hypothesis, it allows you to, you have to test it, right? To see if it actually is true. And so if a hypothesis can't be tested, you kind of have to discard it, because the whole point is to generate testable hypotheses and make observations until you can eventually come up with some sort of a grand theory that describes the process. And then again, it's all about making predictions, testing those predictions, etc. And so the goal isn't to reach absolute truth, which is impossible. It's not something we can do. It's basically saying this is what we think we know based on the observations we've made so far. And you have to be able to make new observations to allow science to progress. And you can't hold on to your ideas on how you think some things work so closely that you're not able to keep making progress. So there's no real sort of, outside of the scientific method, there isn't a formal process for how we go about doing that, other than to continue to make observations, to test them, and try to get to a stage where you have a theory, which is defined here, I think, quite nicely, a well-substantiated explanation of some aspect of the natural world. And so that's what we'll try to learn about